Okay, here again we are going to use tangential normal, and let's say we are going to say given x of t equals, let's say, 5 sine 3t, and y of t equals, let's say, 3t something. Determine let's say the following things: v in Cartesian to magnitude of v let's say a in Cartesian a in tangential normal v dot, and then radius of curvature rho. And let's say all of these at time, I don't know, t equals 1 second. And everything else is an appropriate unit so that you don't have to convert units and so on. Okay. When we plug in t equals 1 second, this is 3t is in radians, and you just evaluate sine in radians. Okay. So in general, when we leave things unstated, just assume that whatever goes here appears in radians, and you just have to evaluate the trigonometric coefficients in radians. Okay. So here t in seconds is given. Okay. Okay. So how do we do these things? Part one is v in Cartesian. Well, first of all, you're given x and y. So v in Cartesian is just v equals x dot I plus y dot j, and that's going to be equal to 5 times 3. Well, first let's perhaps evaluate x dot and y dot. X dot is 5 times 3, and then derivative of sine is cosine 3t, so that's 15 cosine 3t. Okay, and then y dot is just 3. We can plug in t equals 1 here and get the answer, but in any case we have v equals 15 cosine 3t plus I plus 3j. Okay, so let's call this 1, and then of course the answer at t equal to 1 second is going to be v equals 15 cosine of 3I plus 3j, and this is actually the answer for part 1. That's the answer for part 1. But this is going to be useful because we're going to be differentiating velocity to get acceleration at time t equal to 1. But when you differentiate that, we need to make sure that we are differentiating the function of time, and we are not differentiating the constant the velocity value at that particular time, right? So we want to differentiate this to get velocity. In any case, so that's the velocity. How do you compute the magnitude? This is the magnitude. It's just, well, square root of sum of squares. So we have 15 cosine 3 square plus 3 square, whatever that is. That's going to be your answer for part 2. Now we want to get Cartesian accelerations, for which we just differentiate this expression, right? So let's do that. So derivative of cosine is sine, minus sine, I suppose there's a 3 that comes outside. So we have 3 times 15 is 45. There's a minus sign, so minus 45 sine 3t I plus, well, the derivative of 3 is just 0, so we have 0j. So that's the Cartesian acceleration in Cartesian coordinates. Okay, and of course we can, at time t equal to 1, we can just plug that in, 45 sine 3 I. You can write a decimal answer there. Okay, so now we have the Cartesian acceleration. The next thing that is being asked is what is acceleration in the tangential normal coordinates? Okay, how do we compute that? We have to convert Cartesian coordinates into tangential normal. So let's do that. So we know a equals minus 45 sine 3 I. And then we want to replace this I in terms of ET and EN. Okay, we want to do that. How do you do that? What is the relationship between ET, EN, I, and J? Okay, so recall that ET, the tangential vector, is always along the velocity vector, and it's basically velocity vector divided by velocity magnitude, right? In fact, that is the definition of velocity or the tangential vector, which is the velocity equals velocity magnitude times the tangential vector, which makes sense. So what we need to do is basically write an expression, ET equals the velocity vector divided by velocity magnitude, which is given by 15 cosine 3 I plus 3j divided by square root of 15 cosine 3 square plus 3 square. So whatever that comes out to be, okay? And then we can also evaluate the normal coordinate system. So this just gives us tangential. The normal coordinate system or normal coordinate axis, how do you do that? So before we try to do the normal unit vector, what I'm going to do is actually get the numerical values for these various answers. And what I'm actually using on the side is actually MATLAB to compute the numerical values. I'm just going to first evaluate this, 15 cosine 3, 3j. What is 15 cosine 3? 15 times cosine 3 in MATLAB gives me basically minus 14.85 I plus 3j. And this is all going to be in the standard units, whatever units other things are provided in. And let's say this is in meters. Okay, so this is all in meters. So that's the answer for part 1. This thing, I'm going to evaluate it again on the side. So this apparently is equal to, so you can try to evaluate it on your own with your calculator right now. but I'm getting 5.1499 or 5.15. So for these kinds of questions, 2 decimal places is good. Okay, so sorry, that should have been meters per second. Acceleration, that quantity 45 sine 3. So I'm just using, just to be clear what I'm doing here, I'm just using 3 to be in radians. Okay. Turns out that's equal to minus 6.35. Now it's going to be I, and it's going to be in meters per second square. Okay, so the number is going to be meters per second square. So I'm going to put everything together here. So this is basically minus 14.85 I plus 3j divided by 15.15. And that's going to be equal to supposedly it's 0.98 roughly I plus 0.198 j. Okay, roughly. Okay, and this of course has no units because it's a unit vector. It has no units because it's velocity by velocity, therefore it has no units. Okay, so that's the tangential vector. Now how do you get the normal component? Okay, so rather than try to write an expression for the normal component based on the tangential vector somehow, what we can do is compute first the tangential acceleration, and then the total acceleration minus the tangential acceleration is actually the normal acceleration. So let's do that. So so I'm going to call this AN, which is the magnitude of the tangential acceleration is basically A, or component, more precisely. So it's A dot ET, okay, A dot ET, which is, well, I suppose we didn't do 45 sine 3, did we? Well, I suppose we did. So this is minus 6.35 I from here. So what we have here, so this is equal to minus 6.35 I dotted with ET, which is minus 9.98 I plus 198 J. And this is a dot product, right? So you have to be careful. This is a dot product. It's not just multiplication, so you have to be careful. I dot j is 0, so this term goes away. So you just have the product of these two things. So you have 6.35 times 0.98 I dot I plus 0, basically. It's a 0 vector. Okay, 6.65 that gives us 6.223. That's it, right? So this is the component. It's a scalar value, and that's going to be equal to 6.223 6.223 meters per second square. That's the tangential acceleration. And then we can write the tangential acceleration vector equals A equals the tangential acceleration, the component times the tangential vector, plus normal acceleration times the normal vector, okay? But we already know the tangential component and the tangential vector already. So we have minus 6.35 I equals 6.223 times E sub t, which is minus 0.98 I plus 0.198 j, and that's going to be equal to essentially En times An, okay? Okay, so let's sort of rearrange things. So bring this to the side, or basically keep this here and bring everything to the other side. So you have minus 6.35 I plus 0.98 times 6.223 I minus 0.198 times 6.223 j. We can try to simplify this a little bit. So I'm using sort of MATLAB on the side to do these calculations. .98 times 6.223 minus 0.198 times 6.223, and I'm getting something like minus 0.2515. I guess you can remove a couple of digits there, but whatever. And then minus 1.23j. Okay, I guess if you want to remove these things, that's fine. So that's basically A sub n, E sub n. What does this mean? So this whole vector along the normal direction of the acceleration is this quantity. So An itself is going to be the magnitude of this. An is going to be 0.25 square plus 1.23 square, whatever that is. That comes out to be 1.26 meters per second square. And then En is going to be basically this vector divided by this vector, basically the unit vector along this direction. Which I'm calculating offline. And supposedly it's equal to minus 0.2 I plus or minus 98j. So that's En, okay? If you want, okay? But we were asked the total acceleration along the tangential component, normal sort of component. So basically what we have is A equals the tangential component 6.223 ET, An, which is the normal component, 1.26 En. So this is actually the answer. This is not relevant, at least for, this is not relevant for at least this thing. Once you've computed the magnitude of the acceleration in the normal direction, you're kind of all set. So the total acceleration is the tangential component plus the normal component, and we evaluate each of those things, and that's what you have. Any questions about this? So what have we done so far? We've done all the stuff. So far, we can also get v dot and radius of curvature rho. What is v dot? We already have computed it. V dot is the tangential component of the acceleration. Okay, so recall A is v dot et plus v square over rho en. So implies this is part number 5, I suppose. V dot is 6.223 meters per second square. And part 6, it asks for rho. And this is a problem that we've already solved. We know the magnitude of A, we know v dot, we know v from earlier. We need to find rho. So we use the magnitude version of this to find rho. That may be easiest. We can actually, well, there's a few ways of doing this, I suppose. You can use the magnitude version of this and find rho, or we can just use 1.26 and the velocity value to find directly rho. So I suppose we can use either one. Let me just write one of them here. Use this, or use an equals 1.26 equals v square over rho. So basically we have 1.26 equals v square over rho. What is v? We already computed, 5.15, 15.15 square divided by rho. So rho equals 15.15 square divided by 1.26. I'm going to compute. Let me just make sure it's 15.15 there. Looks like it. So 15.15 square. I'm doing this offline here. 1.26. 182.16 or something. Okay, so that's how you solve this problem and sort of convert Cartesian to tangential normal and vice versa, as the case may be. Of course, a particular problem might not exactly follow this procedure, but you kind of get the idea of how to manipulate these things. The main idea is that the velocity direction is the tangential direction, so you just get the unit vector in that direction. And then once you get that unit vector, you can compute the tangential component of the acceleration if you want. And then the total acceleration is the tangential acceleration plus the normal acceleration. If you know the total acceleration and then the tangential acceleration, you can compute the normal acceleration and then go from there, okay? Let's stop there.